It's time now that we take a look at natural logarithmic and exponential functions. Now, like usual, I would take a look at the learning objectives for this next several videos. What's the key things we want to get out of this? We want to be able to develop and use properties of the natural logarithmic functions. I want to understand the definition of the number e. E is kind of a cool number. I want to find derivatives of functions involving the natural logarithmic functions. So I want to take derivatives of logs. I want to develop properties of the natural exponential function. I want to be able to differentiate the natural exponential function and integrate natural exponential functions. So now recall, if I would need to integrate something that looks like x to the n dx, I can use that general power rule and just simply add 1 to the denominator and divide by, add 1 to the exponent and then divide by n plus 1. And this works very well as long as n is not equal to 1. If n equals 1, we have an issue, or if n equals negative 1, we have an issue because negative 1 plus 1 is 0. So I get x to 0 divided by 0. Obviously, there's an issue. So how do I handle a situation where I have an integral that looks like x to the negative 1 dx, which is the same as the integral of 1 over x dx? Well, the way we handle that is by the natural log, because the natural log, which we denote by ln x, this is defined as the integral from 1 to x of 1 over t dt. Now, I want you to take note to this t here. This is a dummy variable. Whenever I integrate, I'm really integrating with a dummy variable. It doesn't matter what I put there. I could put smiley there if I want. It's not relevant because when I integrate, I'm going to replace it with the values that are in the bounds. In this case, I have a numerical value and I have a variable. So when I integrate this, I'm going to end up with a function of x, which is actually ln x. Now, this integral also tells me, by the one of the fundamental theorems of calculus, this also tells me that the derivative of ln x, what that must look like, because dx of ln x must be equal to 1 over x, which brings me back to here. So consider y equals ln x. Then dy dx is the derivative ddx of ln x, which, as I said, must be 1 over x. Now, if I have a situation where I have the log of a function of x, not just x, because obviously if I apply the chain rule, the derivative of x is just 1. But if I have g of x where it's something other than simply x, it's some function of x, then by the chain rule, the derivative of the log of g of x is going to be g prime of x over g of x. And that's really what I have here, because I can think of g of x as simply equal to x, and so g prime of x equals x prime, which is just 1, which is exactly what I have written there. It's when g of x is a little bit more complicated than simply x that I really need to worry about it and think about what that derivative is actually going to be. Now, I'll work out some examples in a little bit, but this is just an introduction to get you up to speed on a couple of definitions and give you an idea where it is we're actually heading.